So hi, today we will talk about push-pull converters. Again, it's another popular type of DC-DC converters. So the topology looks like that. So it has a kind of non-conventional transformer. So here, what we see is normally they use a center tap transformer, and if you don't remember it from last year, so it is you have a transformer, normal transformer, but you have some connection just in the middle of those terminals. So you can also think them like having two independent windings on the primary and secondary, but they are electrically connected. So this is center tap transformer. So you can Google it if you want to investigate more. So here, like we have a center tap transformer. So again, it is not like they have like separate cores. They are still like sharing the same core. They have the primary one, primary two, secondary one, and usually they have the same number of turns. So at the end, we have MP over NS turns ratio. And we have two switches at the primary and like two diodes at the secondary side and an LC filter. So again, just looking through that one, it seems like a buck converter, but we have that section. So let's discuss how does it work. So it has basically three operating conditions. The first one, we can have the switch 1 open, okay, and the switch 2 off, or we can have the switch 2 on and switch 1 off, or in one case both of these two switches are off. So what you don't do is you don't turn on these two devices at the same time. So either you turn off both of them or you turn on one of them. Okay, so let's have a look at the operating conditions. So the first condition that we will have a look at, the switch 1 is on and switch 2 is off. So let's have a look at that one, and in that condition we have D1 is on and D2 is reverse bias. Let's see, switch 1 is closed, so we will have that one. Switch 2 is off, right? So once the first switch is on, we will have some current flowing in that direction. However, that one is open, so there will be no current in that path. But it doesn't really matter because it is the transformer winding share the same core, so that will link some voltage on the both of the secondary voltages. And if we didn't have any diodes, we will have some currents flowing from both windings. But let's have a look at the current direction and the direction of the dots. So once we have that one, that part would like to have some current in that direction, and also that would like to have some current over that direction. But that means we will have some current over here. So let me try to maybe draw it like that. So you can have some current like that, but because of D2, okay, that one is now blocked, so there will be no current on that half. So what we will see is we will have some current flowing through that part. Okay, so once the switch 1 is closed, I will have, okay, normally if we didn't have the diode, it will have that kind of current, but because of that diode, the current cannot flow through the second part of the winding over here, but it parts from that part. So D1 is forward biased. So let's have a look at the voltages, and again it is similar to forward converter during that region. So what we will see is we will have that winding over that one. So the ratio of is P1 over S2, or if they are equal, this center tap, so it is symmetrical, those two windings. So that means we have N2 divided by M1 and secondary divided MP times source voltage is equal to Vx voltage. Vx voltage is the inductor's, not directly inductor's voltage, but that node's voltage. Okay, so what we see is, Vx, it is N2 over N1 divided by Vs, and let's try to calculate the inductor voltage. So inductor voltage is, here we have Vx, on the other side we have Vo, and once you subtract these two, okay, so you have N2 over N1 multiplied times Vs minus Vo, and this is the point where you charge your inductor, so you are increasing its current, and the current increases linearly. So let's have a look at the other operating point, and actually it will be symmetrical. Now we have T2 is on and T1 is off. So let's have a look at that region. So let me clean those parts for now. And what you have in that one is, you have this one is off, okay, and this one is now on. So the current direction now will be like that, right? So you have some current flowing in that case, and in the previous one, remember it was flowing for the winding, it was coming from the dots and going out from this case. Now it is opposite direction. Now it is coming out from the side of the dot, right? So in this case, the current would like to flow like that, okay, but this time that D1 will be reverse biased, so the current direction, okay, the current direction will be through, over, and in this way, right? So again, this is, try to induce voltage, actually induces voltage on both of the coils, but because of that diode, that doesn't cause any current to flow through that part, but you have the other one. But actually from the perspective of that inductor, nothing has changed. Still Vx, okay, Vx is still N2 over N1 times Vs, okay. So again, in this case, it is the symmetrical, and nothing has changed for the inductor, and actually in this operating part, it is still charging up linearly. So of course, we know if you continuously charge the inductor, it doesn't come to a steady state operating point. So that is why we have the third region, where, remember, in the third region, actually what's happening is you turn on one switch, turn off both switches, then turn on the second one. So you call it the region number 3. So we investigated the first and the third, but there's another intermediate region between these ones. These are the cases where we have both of the switches are closed. Yep. Clean that part. Okay, so we have that one is off, that one is off, right? So there is no current either from here or there, and because of that, actually you don't have, that doesn't mean those windings currents automatically equal to 0. I mean, at the end of the day, what is important part is, let me draw transformer core here, because that part can seem a little bit tricky, right? So in a normal transformer, I mean, if you don't draw any current from here, I mean, you can still, run some current through that one. That will increase the flux or charges the LM, remember. But here, like, we have the third winding. So let's see how will it behave. So now, in the region first and the third regions, we charge the inductor. So we have some non-zero inductor, and actually that inductor would like to flow through somewhere, right? So it comes to that part now, comes that part, and actually now it would like to, divide by half. Actually, both of them are coming that way, right? So let's see what is the case in that one. So whatever VS2, look at the current conventions, that one is getting into the dot, but that current is coming out of the dot. So whatever VS2, actually VS1 is symmetrical and negative of that one. So it is as if like Vx will be 0 in this case. And for your transformer core, yes, this is creating some current in that direction, or let me make consistent with the other one. So it is as if you are having some current through here and some current over here. So it is like you have 5 turns creating some flux on one direction, and you have 5 turns creating flux in the opposite direction. So the total, if you calculate, we will discuss that in the magnetic design. But if you calculate the flux, or if you just write the HDL, remember, is equal Ni. Okay, if you calculate the total MMFs in the coils, that will be 0, because the number of turns are equal, but the current direction of each winding is opposite. So we are basically not using it like a coupled transformer, and this is consistent with the first winding, and actually you are not carrying any current. So what happens to the inductance during that region? Okay, so during that region, these are both switches are off, so they share the inductor current equally, and the Vx will be 0 on that side. Okay, so Vx will be 0 on that side, so Vlx will be minus Vo. Okay, so Vlx is minus Vo. In that region, your inductor discharges, okay, and still feeds the load. So it is like a buck converter where you charge in 2 cycles and discharge in 1 cycle. So at the end of the day, it looks like that. So whenever at first first switch is on, okay, and you are charging that one, let's write that voltage. Remember, what was it? It was N2 over N1 times Vs, right? So then you charge your inductor, then this is Vx, and then Vx comes to 0. Let me try to plot the inductor voltage here. So let's use the blue one, is, let's say, Vlx. Okay, so in the first region, it was Vx minus Vo, or in other words, N2 over N1 times Vs minus Vo. Okay, then you have both of the switches are off and off, right? So then Vx will be 0, and Vx will be 0 is equal to Vlx is negative, and that negative value is minus Vo, right? And then you have the same, but the second switch is on, but the voltage is same, and it is coming like that. So the interesting thing is, the full, that is how you make your definitions, but our full switching period, all symmetry is over here. You have the switch 1 off, switch 1 on, both of them are off, switch 2 on, both of them are off, then you complete a full cycle. So in a full cycle, it is like a buck converter, it's like a forward converter, but you make 2 cycles, right? But of course, what you can do is you can still calculate, again in my drawing they are not equal, sorry, but the positive areas and negative areas of the inductor should be equal to each other, or if you take the absolute values, the actual values, they should cancel out. So I can calculate the output voltage waveform, right? The interesting thing is, like, again, from the inductor current point of view, you have like 1 cycle here, but it is actually half of the sampling, half of the TS. Okay, so actually if you think about it, it is better because your switches are operating like at 10 kilohertz, for example, but your inductor current is going up and down at 20 kilohertz. So actually that helps us to reduce the current ripples compared to a normal buck converter or forward converter. So it is as if we doubled the switching frequency, right? So again, normally the off period, if this is DTS, then you have 1 minus DTS, but now the definitions is if this is DT, okay, if this is DT, then another duty cycle here, DT, and these are off periods, and that's called consistent, and these are delta, and delta is 1 minus 2D divided by 2TS. Okay, so again, you can actually do, that's all symmetrical, so you can calculate the inductor voltage area in these 2 areas, or you can combine all of them to you, and actually I leave it as an exercise for you to calculate. And what you can find is it is as if it's a buck converter, or it's like a forward converter. So again, we have N2 over N1, the voltage ratio, and we have the D as the duty cycle, but we have that 2 term, because again, if you think of it like if this is DTS, in 1 full cycle, you have 2 regions, 2 times DTS regions where you send energy, and output voltage is equal to ratio of these 2 regions. So that is why we have 2Ds. Actually, you can calculate it mathematically. All right. So that is 2 times N2 over N1 times D. It is exactly the same. It is twice of the forward converter. And if you think about these 2 D regions to be same, so it is exactly same with the forward converter. So the biggest advantage of push-pull converter is they utilize the magnetic core better. So what does it mean? So remember, in a forward converter, what we have is you have some charge in the magnetic core, and you are giving some positive current. So if this is your flux or flux density, so you are only operating in the positive region, then you are discharging your core. Again, if it is ideal, then it discharges completely. If not, then you will still have some remnant flux density. But at the end of the day, you are working only in this region. Okay, in a forward converter, because of the topology, you don't apply negative current to the primary winding, so that will result in the total energy transferred through the magnetic core is limited to that region. However, in the push-pull converter, what we are doing is first we are giving some current in that direction. Remember, there are like 2 windings here. So let's say the flux is created upside when the switch 1 is closed. Then you close both of them off, so you are staying there, so the diode is like freewheeling, then you are applying some negative current, and actually during that one you are applying a negative flux. So if you look at the BH characteristics, okay, if you look at the BH characteristics, so we are actually moving between these regions. So we are using both the positive and negative regions. So that will help us to utilize the core better, or you can use a smaller magnetic component to transfer the same amount of energy, as you will see. Okay, so that's why, you know, they are becoming quite popular. Actually, the disadvantages, you have two switches to control, so, you know, MOSFET drives or that kind of controllers can be more expensive, but the magnetic core can be better utilized. And actually, you know, I know probably in your hardware project you will use either a forward flyback, or you can again use a push-pull converter. And actually there are like many design guides I uploaded to the course web page, so please have a look at all those links. They are all very helpful. Okay, so that's all for today.